We're all trying to get a handle on the future, right? From figuring out if it's going to rain to playing the stock market. But what if I told you the key to understanding all that chaos, all that unpredictability, wasn't some ridiculously complex formula, but actually just three simple, common-sense rules? Well, that's exactly what we're going to dive into today, the surprisingly simple foundation of all probability.
It seems like a total contradiction, doesn't it? How on earth do you make rules for something that, by its very definition, is supposed to be rule-free? That's the puzzle that had thinkers scratching their heads for centuries. How do you build a logical system for something that feels, well, completely illogical?
So to even begin to tackle this paradox, we first needed a whole new way of talking about it, a new language. For the longest time, our ideas about chance were just based on gut feelings. And yeah, that worked okay for simple coin flips or games, but it just completely fell apart when faced with the real, messy world. This slide really just lays it all out. The classical way of thinking, the one we all learned in school, good outcomes over total outcomes, it's neat, but it has this huge catch. It only works when everything has an equal chance of happening. But what about a loaded die, or the chances of a stock going up? That's where, back in 1933, a Russian mathematician named A.N. Kolmogorov came along and pretty much changed the game forever.
So what was Kolmogorov's big idea? Well, it was actually brilliant. He realized that we could use the language of set theory, yep, the same stuff with the circles and boxes you might remember from math class, to literally map out the entire world of possibilities for any random event. And the best tool for the job? The good old Venn diagram. Okay. First things first, we have to define our universe. In probability, we call this the sample space, or just S. It's nothing fancy, it's just a complete list of every single possible thing that could happen. So for a six-sided die, the sample space is just the numbers 1, 2, 3, 4, 5, and 6. In our Venn diagram, this is the big box that everything else lives inside.
Now, inside that universe, we're usually not interested in everything at once. We care about a specific outcome, or maybe a group of outcomes. We call that an event. So for our die roll, an event might be rolling an even number. That would be the set containing 2, 4, and 6. On our Venn diagram map, an event is a circle inside the box. It's a specific destination we're focused on.
And this is where the real power of set theory kicks in. It gives us this super precise visual language to talk about how events relate to each other. Want to talk about A or B happening? That's the union of the two sets, all the space they both cover. A and B happening together? That's their intersection, just that little bit where they overlap. Not A? That's everything in the box that's outside of circle A. And if two things can't possibly happen at the same time, their circles don't even touch. All right, now that we've got our language down, we're ready for the main event. These are Kolmogorov's three simple rules. They're called axioms, which is just a fancy word for fundamental truths that everything else is built on. This is the bedrock of all modern probability. Axiom 1 is about as straightforward as it gets. The probability of anything happening can't be a negative number. It just makes perfect sense, right? You can't have a negative 10% chance of rain. The absolute lowest a probability can go is 0, which just means it's totally impossible. Axiom 2 is just as intuitive. The probability of the entire sample space, that is, the probability that something from our list of all possible outcomes will happen, is 1, or 100%. If you roll a standard die, you are guaranteed to get a number from 1 to 6. It's a certainty.
And now Axiom 3, and this is where it starts to get really useful. It says that if you have two events that are mutually exclusive, meaning they can't both happen at the same time, their circles don't overlap, then the probability of one or the other happening is simply what you get when you add their individual probabilities together. Easy as that.
Okay, so let's see these rules in action. We're going to take these three simple axioms and use them to build one of the most important tools in all of probability, the addition rule. And we're going to see exactly how it works with a really simple visual proof. That third axiom is awesome, but it's got that one little condition, right? It only works for events that don't overlap. But what if they can? I mean, what's the probability of drawing a card from a deck that's either a king or a heart? Well, the king of hearts is both of those things. So now we have a little problem. So here's the issue. If we just blindly add the probability of getting a king to the probability of getting a heart, well, we've counted the king of hearts once as a king, and then we've counted it again as a heart. We've double counted that little overlapping section, the intersection of the two sets. The solution, honestly, is so elegant. To fix our double counting mistake, we just have to subtract that overlap one time. And just like that, we've built the general addition rule. The probability of A or B happening is the probability of A plus the probability of B minus the probability of them happening together.
You know, this quote really gets to the heart of why this axiomatic approach is so powerful. What it's saying is that the beauty of these rules is that they are pure logic. They don't really care what we think probability means in the real world. They are just a consistent set of rules that always work, and that's their genius. So, why should you care about any of this? A bunch of circles, some axioms. What's the big deal? Well, it's because these three incredibly simple rules give us a rock-solid toolkit for understanding one of the most fundamental forces in our universe, chance itself. These three simple rules are literally the foundation for everything from how your weather app works to how financial markets are analyzed. They're the engine running under the hood of modern data science and AI and machine learning. They give us a real, mathematical way to reason about our uncertain world with a stunning amount of precision. Kolmogorov showed us that even something as wild and chaotic as randomness can be understood and described with just a few core principles. It really makes you wonder, doesn't it? What other huge, complex ideas out there are just waiting for someone to come along and find their own simple, hidden axioms?